Okay, hello everybody. Good morning, good afternoon. We're going to pick right up. We spent quite a bit of time on the simulations last lecture, which was the pre-recorded one. If you didn't get a chance to look, you'll know what I'm talking about when you do. And I have to apologize, lecture 2, I am fighting with YouTube. I think I kept uploading one that I already had or something, but I'm not sure that it wasn't at fault, but in any event, it kept deleting the video I uploaded, and somebody would tell me, and I would upload and walk away, not wait the 10 minutes for it to finish, and finally figured it out, I think this morning or maybe late last night or something, which would have been late yesterday your time. So I think they're all out there. I've even renumbered number 5 to number 5. I had it numbered 4 earlier, so I'm getting in the groove of this new tool, and I would love to know if you guys are happy with the way YouTube is working on this, and especially if you're not, because the tool I've used in the past is called Vimeo, and I will probably discontinue using that if YouTube is working for you. All right, so to dive right back in where we were before, I've added about 25 slides to what we've had in prior semester because of a talk I wrote on a particular type of attack, and so we're going to take a look at that. But let's get a running jump at it again. What we talked about last time in this lecture was kind of the basics of the internet, and if you'll remember, this was the beginning of the lecture on halfway through chapter 1 with delay and loss and protocols and layers, and so that's where we are right now, is the protocols and layers. And in the internet we have 5. Remember the mnemonic: please do not data link, take advice. Please do not take advice, the first letter of each of these things. And so the physical layer is the bits. The link layer handles most of the technologies for LANs that you've ever heard of, from Wi-Fi to Ethernet, and it's 802.11 unless they've done another 100 since I was looking. The network layer is where IP exists. The transport layer is where we have TCP or its evil cousin UDP. And then most of the things that we ever use are at the application layer. So if you're asked what layer something's at, when in doubt, guess application layer, because unless you know otherwise, that's usually correct. So the network layer, the transport, applications, and link, they all have addresses associated with them. So this would be like you having a social security number, your house having a telephone number, that your apartment having a telephone number in it, with the apartment number on the outside. Maybe the phone's in your room. The apartment has a number. The building outside has a number. The area has a zip code, etc. So there's layers of numbers that are used in lots of things, and that's also true for this. So when we start getting into addressing a little bit later, I'll reinforce this again, but just understand numbers are really critical at separating one stream of communication from another, or one device from another at a particular layer. So think about driving. Just like license plates are useful for separating one vehicle from another, it's not enough to know who's driving, right? So you need to know more. You also need to know the driver's license of the person inside. All right, so we want to talk a little bit about how this gets used and why we have these layers. We talked about the airline model a little bit before, and here's a walkthrough of what happens when a source wants to send a packet of information to a destination. The application produces a piece of information that we're going to call a message, and it hands it down via a function call through a library called a socket library to the transport layer. The transport layer is some software that's running in your operating system that allows you to pick whether you want a very reliable, well cared for packet delivery, or if speed is of the essence and you're willing to go with something lightweight. So the application has a process ID. At the transport layer, we use an address called port numbers to kind of keep one stream of packets coming from one application apart from the other, because they're all flowing through this software, so it needs to keep them apart. The network layer is where IP addresses exist, and it has a whole other set of responsibilities to perform, and that's why it's in its own set of software that runs in your operating system. So these things get handed down, and then they'll eventually make their way to the link layer, which is where, say, Ethernet lives, and you have hardware addresses to keep one device separate. So when you drop a packet on a Wi-Fi network or you drop it on the wire on Ethernet, everybody can hear it. How do you know if it belongs to you? By seeing if the address matches. So you need addresses at this layer as well. One key thing to remember is there's one way in and out. So when you draw these diagrams, whichever layer you start in, let's say I ask you, show me what happens from the transport layer between computers, it's never directly across. It's also never down or up at an angle. There's only one way out, and it's through the bottom. And you can make your way from there over to another device, but you enter that next device, again, through the physical layer. That's the way in and out of these computers. All right, so let's walk through. Here's the message. When I get down to the transport layer, I need to add a little more information to the front so that when I get something back later, from the other end of the network, presumably I'm going to get packets back in response. I need the transport layer to be able to still remember that the answer belongs to me, because there's lots of things going on with the network on my computer, not just my application. So I add a little extra information to the front to remember, and I hand now the combination of these, the message and the transport header, down a layer, where there's another header added on for the information that the network layer needs, and finally one that the link layer needs. And this isn't quite technically right, because the link layer, some of the more popular technologies actually put something on the end as well. But this collection with all of this extra data in there is now ready to be sent down to the physical layer, and it's all being done on behalf of this message from the application. So I send something physical to physical. It's an Ethernet cable, it's a Wi-Fi connection, it's a piece of fiber, it's a phone line, whatever it might be. And in this case, I'm going to get to a device that's a switch. And here we start to see a little bit of the confusion in the industry over the years. A packet switch is the generic term for a router. And we're going to call it router from now on, because there's a less capable but still very important device that we need that doesn't do everything a router does, but it still does a lot to manage networks, and it's just a switch. And the difference between the two is the router has the network layer software running in it, which is a big deal. It's complicated, requires a lot of knowledge to program it. It's a very specialized skill, and we want to get as much done as we can with these switches, because there's not enough money to go around and not enough programmers to go around. And the switches do a lot of things. In fact, we can do with fewer routers. Can't get rid of them, but we can do with fewer of them by using switches intelligently. So at the switch, it only goes up to the link layer. So what that means is when this packet arrives, it's just arrived over the network from here into this layer. It's going to arrive at the physical layer. It'll work its way up. The switch will be responsible for moving it on to the next leg of its journey, but it's kind of a passive. It's not going to look at IP addresses. It's just going to use hardware addresses, and it will forward this item on to whatever the next physical link is. So there's a physical break in the cable here, and here, and here, and here at each point. So I have on this network 1, 2, 3 links, 3 cables, 3 point-to-point connections. And it could be Wi-Fi, in which case it has no cables, but it's still between 2 points, between one device and the next. And when I'm on this first link, I don't know about anything else in the world except what's on this first link. So I have no view, for example, of what's happening over here or what's happening over here. I can't see these devices. I don't know what addresses they're using. I don't know what technologies they are. And, excuse me, and I don't care. So I'm just concerned with what's on this particular link. And the same is true for the isolation here. Once my packet makes it down to the next layer, it's going to work its way back up, this time inside of a router. And so I will pull things across and send them back down, and finally get my way over to the other end where things can be sort of looked at. So let me explain how the reverse is happening. It's actually happening here and here as well, but we didn't draw all those intermediate steps. So once this whole thing arrives at the physical layer, the data link layer is responsible for making sure it arrived without being corrupted, and that it arrived as a whole complete Ethernet frame, let's say. And if it did, then it will throw away the Ethernet header, and it will hand up what remains to the next layer up. And the next layer up is the network layer. The network layer expects to receive something back that looks exactly like what this guy sent in the first place, which is going to be the original message plus the header from the transport, and the header that the network layer over here added on. So these should be equal to each other. If they are, then he will figure out which transport program to hand things to. That's part of the info. He'll strip off his header and he will hand up to the transport layer, one layer higher, exactly what the transport layer here issued. So this is like, I want to send you an envelope. I'm in Germany. Let's pretend it's 30 years ago, and we're going to do old school with a letter. So I take a card, I write you a note with your grade on the first homework, and I take it to a person around the corner who is kind of the office assistant, and I say, hey, can you send this to Andrew or Bradley or Michael or Payne or somebody in the class? And they're at the University of Houston. She or he says, sure. And they will take that and put it in an envelope. I have it in one that just says, let's say Bradley, for example. They'll take it and put it in one that goes with other envelope to the central mail room, but it's with a bunch of other stuff that's going to the University of Houston because we collaborate all the time. We're constantly sending things back and forth. It gets down to the mail room. They look at it and they go, okay, this envelope goes to Houston, and they gather it with some packages that go there as well, and they put it in a box, and they put a DHL label on it. And DHL comes and picks it up, and they put it in the truck with everything else in there, and it gets back to the station. It goes into a container that's getting on a plane that's flying to Houston. So lots of other stuff going there. When it gets to Houston, the reverse starts to happen. So I took my envelope, my note, I encapsulated it into an envelope, which got encapsulated into another one, and then into a box, and then into a truck, and then into a container, and then into a plane. And then it got reversed at the other end. So that's the idea behind encapsulation and decapsulation. All right, let's switch gears now and talk a little bit about network security. It's a huge burgeoning field, and so I've added quite a bit to what the textbook had on this, which arguably might be beyond an introductory course, but I don't think so anymore. If anybody tries to get into a role in networks and doesn't adequately address security, you're going to just get crushed. So I do want to sort of show you, give you some sort of feel of the degree of sophistication that's out there. You don't even need a networking or a computer science degree to understand most of these slides. So I'm confident I'm not going to swamp you with stuff that's too detailed, but I hope it's something that's interesting. So the internet was designed without much security because everybody trusted everyone, right? We were all friends. Can't we all get along? And we've been playing catch up ever since. So security is a consideration. This is the key point on this slide. It's a consideration in all layers. It is not just the application author's responsibility. It's not just the responsibility of the transport layer or the hardware layer. You need an integrated security approach that ensures that each layer provides the appropriate level of protection. So how do attacks happen? Well, one way to do it is to drop bad software on computers on the network. You can get it as a virus or a worm. The difference being a virus, once it gets into a system, it sort of self-replicates itself and will maybe send an email message out to everybody in your contacts saying, hey, I'm stuck and I need money. I hate to ask for this. How many of us have clicked on one of those in our careers? A worm, on the other hand, is passive. It self-replicates itself by getting run. And malware can control, whether it's a virus or a worm, keystrokes and where you've been visiting. If it can control keystrokes, if it can record keystrokes, then no amount of security after that matters. Even if you have an encrypted connection to your bank, if they're grabbing the keystrokes off your keyboard, that's not encrypted. So they can learn everything they need to learn about you. And an infected host can be also recruited unwittingly to become part of a larger attack scheme called a robot network or a botnet, and that's what's used for things like spam and DDoS attacks. So we're going to dig into DDoS attacks for a few minutes here. They are 44 years old, and what they represent is an attempt to deny you the ability to get regular work done. And they typically do it by trying to overwhelm a resource. They began by trying to overwhelm network resources, but now it's targeted at applications as well. And it's been changing a lot in the last few years. So we'll talk about a little bit about what that means. The book uses a diagram like this where basically it's malware, and the way malware would work is you load software, you get people to click on a link, or you get them to visit a site or something, and maybe completely unbeknownst to them, they end up loading a program onto their computer. And at some appointed hour, that program wakes up. Maybe it knows when to because it checks in periodically with some mothership someplace. And it wakes up and starts what we would consider to be an attack, but what the person attacked would consider to be just a really busy day. So if all of us decided to show up at McDonald's, let's say there's 300 people, and we all decide to show up at McDonald's at the same time because we have a bone to pick with them and we want to maybe send a message to the manager or something. Who knows? I mean, I don't know why anybody would have a beef, no pun intended, against one of the restaurants on campus, but let's say we did that and we weren't really interested in ordering food. We might ask for a cup of water. We might ask a lot of questions about the menu. We might then say, well, let me think about it for a minute and then move on. It's not going to be apparent immediately what's going on, but pretty soon the manager is going to figure out something is wrong because there's a lot of people here consuming resources that don't really appear to be legitimate customers. I mean, at first they look like they are, and I can't tell by looking at them, but I'm slowly figuring out, first of all, because I have a line that's 300 people long, that's really unusual. And I might notice that I have regular customers who are not getting serviced in time. So what would a restaurant normally do to combat a long line? You open another register. Just like a grocery store or a shopping store would. You open another register if you want to stay in business for very long. And if you've got enough resources to expand the number of registers sufficiently that you can get the line back down under control, then you can make it through this attack. And that's a strategy for making your way through one of these DDoS attacks. So malware reproduces itself. Here's a little bit of a timeline. As I said, things have been changing. We've been seeing a reduction on attacking networks and a big increase on attacking applications, hundreds a week. But it's been quite an interesting history as this thing is going on. What exactly is being attacked? Well, for the time when I wrote this talk, I gave something that you guys already have seen, which is these layers in here. Other types of attacks besides DDoS, before we turn back and get into more detail, there are things like denial of service attacks by ransomware overwhelming the software and attacking the hardware, but there's other things out there like ransomware specifically. And there's a couple of kinds of ransomware making their way around. One of them you've heard of, which is I've encrypted your system and you either give me money or I'm not going to give you the key. And somebody says, well, can't you turn off your system once go to a backup or something that you have? And so my answer back to them is, how do you know your drive's not being encrypted right now? How do you know what's not happening is we list your files from the least recently used up to the most, and there's a program running right now that's been running for a week that's encrypting all your old files. And there's a program that they've installed that if by chance you ask for something from one of these files, this program decrypts it for now on the fly and gives it back to you, and you can't tell there's anything wrong with it. And once they've made their way all up to the top, they get rid of this, and you're stuck with the file, with a drive full of encrypted files. So how are you going to know if this takes weeks? How many backups do you have? So this has caused people to change the way that stuff works. But with DDoS, there's network layer and app layer attacks, and there's two categories, amplification and non-amplification attacks. So what kind of software are they attacking? Well, just about everything you've ever heard of. This is just programs that run with one of the two protocols at the transport layer, and there's tons of them. And one of them in particular that I'll mention briefly is a memcached attack. But there's attacks that take that try to overwhelm your ability to use DNS requests, and other ones that try to overwhelm NetBIOS, and ones for remote procedure calls, and character generation, and all kinds of other things. But most of us have heard of domain name system DNS attacks, but one of the newer ones this year was memcached. And an amplified attack is one where you talk some host with a very short request into responding back with a lot of data, and not responding back to you, but responding back to who you claim you are, which is really the target. So let's say I come up to you and say, hi, my name is Jaspal Subluk, and let me help you with the mute question you've got there. You're not making any noise though, so relax. Let's say I tell you that my name is Jaspal, who is the department chair of our department at the University of Houston, and I would like for you to call and leave me a voicemail reading the front page of the New York Times completely. And you're like, okay, so you do it. So I left a very short request for you, and what you end up sending to Jaspal is much, much larger. So that's an example of an amplification attack. I got you to send a lot more data than I could send to Jaspal by myself because there's 100 of you. I send this request to a whole bunch of people, and so Jaspal comes in and his mailbox is full, for example. So this can get bad. In the case of a memcached attack, you can have 50,000 times the amount of data that comes back than was sent. A direct attack is one where I don't try to hide who I am and I send information directly to a target. That's dumb because you get in trouble. A botnet attack is where I send messages to a bunch of these people who have been enslaved by unwittingly downloading the software, and they in turn attack the target. An amplification attack is one where instead of loading illicit software on all these users, I make perfectly legitimate requests like, give me this web page, or give me a list of the following hosts from your database. Things that are normal, regular types of requests. And so these are even harder to find because nobody's loaded bad software on your machine. I just send a little request, but I do it in a way where you think it's this person making the request, and you all end up sending your information to them, which they're going to view as a denial of service. So it was a very famous one February of this year with a site called GitHub, which is a site to trade code and discuss programming techniques and things like that. And this made the news as much because of how long it lasted as it was in the news because of what was happening. It lasted for all of a little over 10 minutes. And it took them a little while to figure out that an attack was going on. But once they did, they turned to a service provider, another company that they had a contract with ahead of time that is willing to step in and help if one of these things starts to happen. And that's the real news, that they bothered to have a contract and be prepared. Lots of people don't do anything until the problem's already happened as well. So how did this attack played out? They got 100,000 of these web cache servers, which you'll learn about in the next lecture, to respond back with web pages. And it's a problem because let's say I'm a server supporting U of H. I should only be answering requests from inside the campus. But what this server, like 100,000 of its peers, was configured to do was respond to anybody who wanted to ask, do you have a copy of this object from a website? I mean, why not? If it's a helpful thing to give someone, so if you show up with a request for it, why not help if I can? And the reason is I showed up pretending I was someone else. So we recruited these web caching servers who had inadequate authentication. They weren't supposed to be doing this anymore, to all respond back, and they overwhelmed GitHub. So it was one of these things. And so what their service provider did is they stepped in with a bunch of their own servers. And you'll also hear about in the next lecture content delivery networks. I think that was today. It may have been the previous lecture. They're starting to run together already. But the content delivery networks, they build a parallel network. And if you don't know what I mean, wait till you hear the next hour and it'll all become clear. And these are a type of providers that have lots of servers all over the world. And when you ask them, when you let them know what's going on and ask them to step in and help, the first thing they do is tell people, I am GitHub. So any packets for GitHub, send them to me. And they're in every ISP around the world. So the traffic that's coming from these sites isn't going to go very far. It's not going to make its way across the internet. It's never going to make its way to GitHub. It's going to make its way to this server where they scrub the data and they drop it on the floor. So the ISP is okay with this because it keeps the data from swamping the ISP's network as well. And after a few minutes, the attackers gave up. So it was a spectacularly successful remediation of doing this. Lots of different kinds of attackers out there. We don't really have time to go into it now. Maybe we can come back. The scary thing is you can hire these people to launch these types of attack using PayPal. And here's the prices that I found as of a year ago out on the internet, a couple of years ago. One of the biggest sites sort of put itself forward as we are a stressor, as we call it, somebody who can stress test your network to see how good your DDoS defenses really are. So if you can hire us, we'll launch an attack and we'll help you figure out if your network's capable. That sounds legitimate, and there are some companies who will legitimately do that. But they're not going to do it unless the company themselves hires it. These guys I could pay to attack you, and they would launch an attack. But nobody's clean in this. There's botnet attacks launched from all over the planet, most notably China. When you see numbers this big, you either got to figure out that they're just terrible at security or it's state-sponsored. Doesn't matter. It's everyone's in on the act. There's a bunch that come from every place else as well. The next few slides, if you want to look through them, just basically show you how things are changing. This one basically shows the vast majority of attacks are under 30 minutes, and the number of people who are attacked a lot of times each month was about the same as the number that only had a single attack. So nobody's really safe here. The max, somebody had 242 attacks that they reported. So this would be like coming to work every day, and for breakfast, lunch, and dinner for that month, you have an attack that's launched against you. We've seen a change in shape on the distribution of application and network attacks. We've also seen a variety of different devices on the network inside your organization attack, from your firewall to filling up your internet connection to you're looking at your database server, et cetera. One really interesting case study that was reported by one of the security sites talked about how a customer had a piece of equipment here that was very good at filtering out these types of attack messages as they were coming in. And so they put some of their devices behind this, thinking these are the things they need to protect. But they still had some things in front. Like, for example, they had a public web server out here, and maybe they had DNS, I can't remember, maybe a firewall out here as well. And they were just getting the snot beat out of them. And what they figured out with the firewall is firewalls add rules for people who are bad that they want to filter. So as this firewall started noticing these patterns, it started marking sites on this list, writing them down, saying, no more traffic from you, no more traffic from you. The problem is the firewall only has room for a couple of 100,000 entries, and it was getting full. And if the firewall gets full, everything stops. So this is a company that's trying to keep data going out to the internet while this nonsense is going on. So the first thing they did was they moved it forward one step in front of the firewall, and that helped a lot. And then they moved it one more step in front of the public web server, which is a sacrificial lamb. If somebody hacks it, you just re-image it. It's not the real one. It's just a copy. And once they did that, the number of rules their firewall had to deal with dropped within 15, I don't know, this looks like actually within 4 minutes, from 552 to 556. So this is another type of remediation. So you may be doing things like this in a network to try and remediate. So it's not all just writing good firewall code. It's not all having a good filter. There's things you actually need to do sometimes in the middle of an attack. So how do you protect things? What Cisco claims is that it stops 40 billion attacks a day for customers by trading rules. So when one customer sees something suspicious and sends it up to the cloud, if it's agreed to by Cisco, then it gets pushed down to every other device on Earth that's part of this cloud as well, and they're all immediately blocked. So that's sort of sounding the alarm. You also have hardware devices that we just talked about. You can call people to get help as well. There's companies that will do that as well. So attacks aren't going anywhere, and you can't really defend against these things anymore without a lot of automation, systems that automatically detect and block for them. So defending without automation is just not realistic. So what the last few of these slides do is they just go over things. These went over things we've already talked about. And now we're going to sort of leave DDoS behind, denial of service attack, and get back to the slides from the textbook. So what was that, a 10-minute jaunt down to give you a little more idea of what's going on? One of the tools that we're going to be using a lot of this semester is Wireshark, which you guys have installed by now. And Wireshark lets you monitor packets as they're happening on a network. And unless you put your program into what's called promiscuous mode, you're only going to see the packets that are really intended for you. And even in promiscuous mode, they're not going to let you see everything. They're not going to let you see the contents of everything, for example. But it's a very helpful tool at spotting, at analyzing what packets actually look like. But it can be used to attack you as well, absolutely. Another one is an IP spoofing, where you send a packet to someone's IP address and they answer back saying, yep, that's me, here's your, what do you need? When it's really not them. There's also a man-in-the-middle attack, and I don't have a slide on that, but that one's actually pretty clever. Let's say, pick on McDonald's again, let's say you go to the student center on campus and somebody meets you at your table with a apron and a bow tie, and they're holding an order form. They have a copy of a menu or something, and they say, hi, welcome, can I get you anything to drink to start off with? And you're like, what's going on? And they go, well, it's been an upgrade. McDonald's has waiters. It's an experiment we're doing with the Hilton School of Hotel Management. And, we've got service. Well, true, I'll take a Sprite. And so they go and they pay for a Sprite for you, and they bring it back to your table. So now you're kind of hooked. So you'll continue on with this process. At every step along the way, ordering, getting your food back, asking for a napkin, etc., you think they are McDonald's. What does McDonald's think they are? McDonald's thinks that they're a customer. They think they're you. So this person's in the middle playing both roles on behalf of the other individual. And it's a very effective guise, because at some point, you're going to give them your money, and that's when they leave. So it's a man-in-the-middle attack, and this can happen on a network as well. If you send something to a website, I can respond on its behalf, and I can go and get the real web information and just pass it along to you. The whole time I'm waiting for the payment page to come up, and for that one, I'm going to generate the HTML and hand it to you, and when you return back, it's coming to me. And maybe I've adjusted the URL just a tiny bit so you don't notice, but the attacks are pretty sophisticated. All right, we have a little bit to wrap up on this chapter, and then we've got some more material still to do in the next one. The rest of this chapter talked about Internet history, and what I'll basically race through here is what we thought the history was, and then a very important correction that's been made to it in the last couple of years. The story as it goes is that Larry Kleinrock, who was working at MIT and had this idea for kind of putting a network together, ended up at the Advanced Research Projects Organization at the United States Department of Defense, and he basically showed how packet switching could be used. And Paul Barron, who was an employee at a think tank called the RAND Corporation, which was funded by the United States Air Force, he was given the task of solving this problem of, what happens if the Russians bomb and I lose, one of these links, and it was my only link back to my command and control center, maybe Looking Glass in Omaha, Nebraska, where I send the command to launch a counterattack. Well, if the cable's gone down and these boxes don't know how to do anything without going and being reprogrammed, then we're going to lose the war. So Paul Barron was simultaneously coming up with this idea of, what if we divided the information into packets but put the addresses on them? So this device here would constantly be looking to see where he could reach. And if this one became unreachable, maybe he would learn, let me redraw this a little bit, because the boxes usually weren't the big risk. The big risk was the cable here. So forgive me, let me go back here. If at some point in this link became unavailable and therefore this site became unreachable, then this guy would have been exchanging information all the time over all of his other links, constantly asking, who do you know how to reach? What kinds of networks can you get to? What are their numbers? Here's who I can reach. And you write some software to kind of eliminate the duplicates. But what would have been accumulated is that you would have learned this guy also knows how to get up to here. So when this link over here became unavailable, then no sweat, you just start sending things this way instead. Right? So that's basically the idea. In the Google Drive, for you guys, I have put, can I share that? Doesn't look like I can. I may have just hung my WebEx. Hold on here, let me dial in. Hold on. Okay, I'm back. Sorry about that. I crashed WebEx, but at least I know how I did it. So let me get back to my video here. And it'll figure out that I'm not here eventually, I think. So let me make myself the presenter again. And with any luck, the slides will come back. Okay, sorry about that. That happens. So if it does once in a while, hang with me. It happens sometimes even when I'm in the classroom and stuff. Okay, so what I was getting ready to do was to share my screen and show you in the folder on Google Drive for articles and reading assignments, which is, here's the Google Drive. If I go down into articles and reading assignments, I've reorganized things a little bit, and there's now a history folder. Here's Paul Barron's paper from the Rand Corporation in 1964. Here is the recent history that was the most convincing story by someone who had nothing to gain or lose by reporting what they knew, who was there as all of this stuff happened. He was at the conference, he was hearing the papers, he knew who came on stage first, what day people were there on, he knew the presenters, etc. And so this is the most convincing sort of revision to correct what a lot of people thought was an invention basically by Paul Barron at the Rand Corporation. And I thought so too for the longest time. So it's short, it's a blog post. I didn't write a book or anything, but it's very, very interesting. Then there's some more famous or prominent histories, one written by Larry Kleinrock, but Larry Kleinrock has something to lose, so that one is maybe, I'm not going to say suspect, but it's a point of view that I don't think is as neutral. And then Barry Leiner, who ran the University of Southern California's Institute for Advanced Computer Science, and I think that's where that was housed. I know ISI was. He and these other guys also wrote a history, but this is kind of a group effort. Again, I found this one to be one of my favorites, and so those things are out there in case you guys are interested. And I may ask you a question about one of them, but I'll give it to you in an assignment before that happens if I do it. So you basically walk through the history on things. We got another really key idea that we will study this semester from a project at the University of Hawaii, which is very interesting, and it was called Project Aloha, and it dealt with the fact that you could have two people trying to send something to a third one, and they don't want to interrupt each other, except there's a giant volcano in between, and they just can't hear each other. So what do you do in a situation if you only can have one person communicating at a time, because it's a shared set of radio waves, but the two potential senders are hidden from each other? So AlohaNet came up with the elegant solution that's the basis of what we still use today on Ethernet. And then Vint Cerf and Bob Kahn wrote TCP/IP and were kind of the original architects. Those are the guys I worked with on a couple of projects briefly that I was mentioning, and then we were kind of off to the races. So it started with just a few nodes, and then we got up to 200, et cetera. It's fun because if you Google for some of the early ARPANET diagrams, I mean, it's quaint. You know, they're just like little maps where somebody hand drew these things. Is quite funny. All right, so we've gone kind of blasted through the history. I've already talked about Wireshark. We're ready to move on to the next. Programs communicate with each other. We'll take a look a little later in the next lecture at some other protocols, starting with the one that we use for web browsing, but we're going to dig a little bit deeper here. So the book kind of starts at the top and works its way down, meaning it starts with the application layer and kind of moves down from there. So examples of network apps are just anything you've ever used that connects to the internet, from email to Skype to YouTube or Netflix to social networks, Facebook, Google, anything that sends messages out there. And there's lots of things that do, which you may not be aware of. Those are network apps. And what that basically means, did I disconnect again? I think I'm still here. Mike, are you still able to hear me? I'm hoping. Let's see. Let me see. I'm going to pause for a minute and make sure Mike can still hear me out there. Can text me if you can. Yeah, okay, great. All right. Now, I love those messages. Please send them. Obviously, I don't always see them right away. So, for example, one of them is the network clock. Your clock gets set automatically. That's a protocol that's running over the internet, a program that's running and exchanging data that you don't even have to worry about starting up or checking. And there's things to discover that a printer is available, or that there's a DNS server available to you. So most of the things we use, we start ourselves, but the operating system has some as well. So the way you create a network app is you want to write a program that runs partly on one system and partly on another. And we've had inter-process communication forever. The ability to have one program talk to another program written by different people, but on the same machine or cluster. And we have had a way of building a message and sending it, asking the operating system to send it to the other process, and doing so securely. And that was inter-process communication. What we basically did is got a little more sophisticated with it and started making things like remote procedure calls. So these programs run on different end systems, but they use the network in the middle to communicate. And what we've been able to do with the TCP/IP software we've written is build a standard set of libraries that require that you don't have to write the code to get this done. And one of the amazing things about this is if you just use the library available to you in your programming environment on your device, and you drop a packet onto the network, and it has the destination address that you've learned somehow, even if it ends up taking a path over the internet that neither your router nor half of the others along the way have ever sent a packet to before and haven't heard of before, it will still make it immediately to its destination. So this would be like picking up your phone and dialing a number in another country that has never been dialed before, that is in a country that no one in Houston has even dialed in the last month. It's rare, but possible. It's not unfathomable, and yet the phone network still knows how to get there. So that's a benefit that keeps you from having to ever lay hands and add any knowledge to any of these core devices in the middle. The protocol has been built where you exchange information on networks that are in your area, so you at least know what's in the neighborhood. You will remember things about networks who have sent you packets before, so you remember visitors to your town. And everything else, if they need to go someplace else, you just pick a default route and you send them. If you need to go to the U.S. and you don't know exactly which road is the best, point them from Canada onto this road. That's probably as good as any other. and you just kind of go from there. Right, so that's a key thing where you create it, and the socket programs will give you a little bit of experience in seeing how that basically works. As far as the programs, there's two ways of building these architectures. Most of the time what we write or use are programs that run between our device and a server. And this server handles lots of different users at the same time. And examples would be every website that you go to, Dropbox, the Skype server, your email at Google, Netflix. That's an example of a client-server environment where the server needs to be able to handle lots of different connections at once. And you communicate with the server directly. The other architecture, though, is called point-to-point or P2P architecture. And this is one that's more unpredictable random pairings of users. This actually drives the telephone companies a little bit crazy because when it's client-server, they know where to put the biggest resources because they know you're going to use a little here. It's mostly going to be downstream. You're not going to use a lot for upstream. So we can configure our networks asymmetrically that way. And we're going to make sure, even if this person only buys, let's say, a 10 megabit per connection at front, the circuit we're going to drop there can be upgraded in 5 minutes to a gigabit per second. You just have to call or click on a link or whatever, and it'll be turned on. It's the same fiber either way, so it doesn't cost us more than that. It may cost us more in electronics that we put there, but we expect you to need to upgrade at any moment, and so we want to make sure the bandwidth's there. But when the place you're getting to with one of these peer-to-peer networks is just somebody down the street, it makes the planning harder. So what a peer-to-peer network does is allow you to exchange information directly with someone without a server. And it's a little bit of a fallacy to make that claim because even if I'm using BitTorrent, for example, and I need to download a copy of the textbook because you've heard it's available as a PDF file, you could find out that one where did I get that? One BitTorrent user has this chapter and they have this chapter, and let's say they have this chapter in the middle here as well. But a different site has this one, and a different site has that one. So you're going to need to go to a variety of sites. So you will open a connection with your software first to this, and maybe a simultaneous one over here, and maybe one of them's down here. That's fine. But how did you know this? How did you know it? Someone had to teach this to you, and of course, there's a server involved in doing this. Someone has to kind of get the ball rolling for you. So it's part client-server, and then it becomes point-to-point architecture after that. And there's lots of hybridized examples in the middle. But P2Ps can create vastly larger networks, and they can do so quickly and on the fly. So once we get these devices sort of identified and we know where we want to send stuff, then the problem becomes how are we going to communicate. So a process is of the program that's running on my machine and on yours, and when it was on the same system it was IPC, but now that it's over the internet we're going to say that we're sending messages to each other. And sockets is the name of the programming library that gives us the ability to do it. It's a function call, and we supply arguments to that function. Things like the name of the host that we're trying to get to, or its IP address, the actual message that we're trying to send, whether we want to send it with protection on or not so that it gets resent if it gets lost, etc., the size of the packet that we're sending, and some other basic things like that. And we make that call, and the socket library takes care of getting it to the transport layer, and then the process continues on. So to your application, it appears as if there's a direct connection between you and the other application. That's the fantasy, the vision that we bring to you here. And so we're trying to let you give me a message at one end, and exactly that message shows up at the other end. Any errors that have been introduced have been corrected and resent. Any packets that were lost have been resent. Any packets that have been duplicated are ignored. Any packets that are arriving out of order are put back in order and given to you. So that's what a wire would do. And so if we want that illusion, we're going to have to make that happen. So to keep packets apart, to keep systems apart from each other, you need to have an identifier. And an IP address, which is one of those addresses, is a 32-bit number. So it's about 4 billion different numbers, which is a woefully inadequate number of addresses for things. So the question is that address enough? If a packet shows up, let's say an envelope shows up from the postman, and it shows up at your apartment building, and it has the correct address, but that's all it has on the front of it. Aren't you missing something? Don't you need to know the name of the recipient so you can call out their name and hand them their envelope? Think of summer camp before phones. You guys probably, some of you may know what I'm talking about. But the mail analogy, it's unfortunate we don't use it too much because it's a very close analogy for the way a lot of these things work. So the answer is the IP address is not sufficient. You need something more. So if I have multiple programs running on the same computer, the computer has an IP address, but each of these things must have some sort of a unique address as well. And what we give them are port numbers. So the combination of port number and IP address are the magic pair that we need. So an identifier to uniquely identify a program has to have both the IP address and the port number. So port numbers, some of them are well known and well established, like 80 for HTTP or 25 for email. Simple Mail Transport Protocol is the name of the email protocol that we use. And if I therefore want to send a message to UMass, then here's the IP address I would use. And we'll talk at a future lecture about how we know that's the number. And then here's the port number that we'll use as well. So the application layer protocol defines a bunch of things. So once I get the connection and I know who the packets are going to, that's not quite enough. I need to know how to behave. I need to know how do I get the conversation going? Do I say hello? Do I stick out an outstretched hand? In the name of protocol connections, if I connect to a server, the way we've written that protocol, it's my responsibility to open the connection and to send the request. But you could just as easily write a program where if you open a connection to the server, then it sends messages. It sends messages back, right? First, you don't start the conversation. You open a connection. Let's say it's a radio streaming site, and it assumes if you make a connection, you're there for one reason and one reason only, and that's to get a copy of all the packets that represent the radio audio broadcast. So it just immediately starts sending you. So you got to document how these things are going to work. The types of messages, the syntax, which is what fields, what values they can have. What do they mean when somebody sends exit? Does it mean close the connection? Does it mean leave this page? Does it mean leave the room? I mean, what are the rules surrounding that stuff? And so these have to be very carefully specified in excruciating detail, and we call that a protocol. Some protocols need reliable service. Some of them don't. Some of them need your help in making sure all the packets get there, that they get there in a certain order without too much delay between one and the other. Some of them just need a certain amount of pretty much guaranteed bandwidth all the time. Some of them need security added on. The bad news is the internet doesn't provide all of this stuff. It provides some of it. What this table shows is takes a look at a few common types of programs like file transfer. If I'm going to transfer a file, I'm intolerant of loss. But if what I'm listening to is this broadcast right now with me talking to you via WebEx, then if some of the packets get dropped, the audio has a little glitch here and there, that's fine. You can deal with it. You'll still hear enough to understand what's going on. Right? So that's the type of analysis. And what we've done on the internet is use two different protocols to make this stuff work. One of them is called TCP, and the other one is called UDP. So TCP is Transport Control Protocol. UDP is Unreliable Data Transport. So what TCP will do, if you give it a message, it will first record a copy of the message, and it will give it a number, another number, and it will send it to the other end, and it will ask for an acknowledgement back to make sure that the packet got there. And if it got there, then it will throw away its local copy and move on to the next packet. If it doesn't get an answer back that it expects in a certain amount of time, it will assume the packet is lost and it will send it again. Right? So there's some responsibility for the receiver to deal with things because packets can get lost or just arrive out of order or duplicated. for example. Another thing that TCP does for us is tries to pay attention to the capacity of the receiver so as not to overwhelm them. Am I sending you too many packets at once? Is your application picking up these packets? Should I slow down? Should I stop? And it also tries to detect when it is overwhelming the network in the middle. Maybe that the site I'm sending things to is just like super powered and it can handle tons of packets, but the network is dying in the middle. It's got issues, there's links down, there's not enough bandwidth, and if I am the one that causes a router's buffer to get full, it can cause packets to drop. What TCP, the way we chose to write it, what it doesn't provide is any timing. There's no guarantee from the time you send your packet it will arrive in a certain amount of time. It's sort of what makes me laugh because UPS provides this promise, and half the time they don't keep it for me. At least I have bad luck. So that's a timing service that it's better to not provide it than to provide it and miss it. They don't provide any security. Neither does UDP. They don't provide any minimum guaranteed throughput. And the last thing it provides is it asks permission to send stuff before it begins. You give it a message for a website, it will go and ask the website, can I send you data? Somebody wants to connect to your program at port 80. UDP, on the other hand, is extremely efficient. You hand it a packet, it sends it. Doesn't make a copy, doesn't give it a number, couldn't care less whether it makes it, doesn't deal with duplicates or lost packets or retransmissions, doesn't do any of that stuff, also doesn't provide security or timing, that doesn't ask if it's okay to do stuff. So it's unreliable data transfer, but it's extremely lightweight. So from the time you hand it a packet, it's immediately out the door. So you'll use this for things like streaming, where you don't care if a packet gets lost, but you'll also use it on things where maybe you care, but time is of the essence, like a message to control a piece of equipment, for example, or an earthquake detection message coming from a remote sensor. You would be willing for that to happen via UDP because it's sort of like if you answer the phone at 911 and somebody starts asking you permission if they can talk, you're trying to like, what's the emergency? Like get on with it. So there's a bunch of applications out there, and for each one of these things, we've had to make the decision on whether it runs on UDP or TCP, right? So we'll look at some in an example, but for the next lecture, we're going to look at HTTP, which is the web browsing protocol, and you will learn right off the bat that it runs on top of TCP. So the last slide for today is just a brief talk on security. When we wrote programs that worked over the internet, the TCP/IP protocol provides no security, so we've had to add a security layer in there. And because the security turns out to be something that lots of programs might like to use, and because we don't want to get stuck with the burden of maintaining it by ourselves, we all agreed to use some shareable security software that any program on your system can use. But the most common user of it is the web browser. And whenever you see HTTPS and the little lock icon shows up, you are taking your messages from your browser, and instead of handing them to TCP first, you're going to give them to this extra layer that will handle the encryption, and that is then what gets given to TCP to be sent on. So this is a separate piece of software that we have to run as an application. And by the way, SSL is very old-fashioned. The modern type of encryption that we want to use now is TLS. And you'll have a Wireshark lab on that. All right, guys, I see Hassam is here. I imagine some of you are probably wanting to hang around and ask a question or two on the homework, so I'm going to get out of your hair. Thanks for the emails and texts and things, guys. As you can see, it doesn't usually matter what time they arrive at. I especially appreciate when you guys let me know there's mistakes, like numbers that don't make sense, and that the video is missing. I mean, I won't catch all that stuff. So when you help me, it helps us all make sure this class is running smoothly. Okay, Hassam, I'm going to make you host. Let's see if I can pull up the right panel to do that here. How are you today? Hopefully
good,
doing well.
You.
Good. All right, change role to host. And when I leave, you will also become presenter.
Okay,
all right, guys, have a great day. and I will see you soon. Bye, everyone.
Hey guys, some of you may know me by now. I am Sam, your TA for this course, so I can be here if you have any questions about homeworks or any other stuff. If I know the answer, I'm gonna let you know. Otherwise, I'm gonna ask Dr. Lang to. Okay, so the first question. Okay, let me check the schedule for that question because if it says it's gonna be released today, but I believe yes because you are supposed to have another homework by today. I mean Wednesday. So the answer should be yes. As I said, I am not the one who designs homeworks. Dr. Lang actually is responsible for that, so I'm not sure exactly. But yes, based on the schedule, you should receive another homework today. But as he already mentioned, always there is an email. I mean, if there is a homework, he is going to send an email to everyone. So you're going to receive in your inbox about notification. Okay, the homework is posted. So don't worry about that part. Always should be an email. Oh, okay. So 5 layers of internet protocol. Sure. I'm trying to just review the slides here to see if he has a slide on this one. So we can go through the slides, otherwise I'll just use my own. Oh, here, yeah. I believe here we have something, but let me see if we have. So in that case, I will just go through these slides. These slides are from 14. So briefly try to recap what he said in his talk. Let me see. Okay, just to make sure I don't miss anything. Okay, so. Mhm, mhm. So as you can see here, in this slide number 10. So basically, if you need to do a communication, let's say I have two nodes, node A or node B, and node B. By node, I mean a computer, a device, or whatever who wants to make a communication. So you have a message, and you're going to send this message to the other computer on the other side of the line. So they designed the protocol so in the different layers. So each layer does something on the message you have, and send it through the network. And this protocol actually makes the real communication. So I'm going to go through each of those layers and explain briefly what's going on in each of those layers. So for now, just assume, okay, so you have an application, you have just a message, you're going to send it to someone else. So the very first top layer is application layer or process layer. Let me see if it has a slide on the application. Oh yes, so here. So application means anyway, when you are going to send a message, you are running an application. That could be a messaging application, as you can see here, or even sending an email application, or the application right now we are using this meeting, WebEx thing. So all of them, they are different kind of applications written for the computers and running on computers. And now these applications want to communicate, wants to send a message or receive a message. So these are the application layer generally means the application who has a message to send. That's the idea. So there are a lot of different applications. Email, as I said, video, chat, Skype, all those applications just belong to the application layer. So now let's say I'm running one of those applications. Let's say a very simple application is, let's say a very simple messaging application. So I'm going to send a text message to my friend. So that's the application I'm running. So my application, let's say I just type in some message on my application, that's hello or something, hello world or the simple text string. So that's the message actually my application, which is a messaging application, is going to send. So that's the application layer. This application layer hands the message to the next layer, which let's go back to the slide number. Let me see here if we have it. Now let me just go back to that slide so we can see what's going on. I'll show you. So now you see, I am on. So again, application layer creates a message. As I said, let's say for now my application is a messaging application. So hands the message to the transport layer. So now transport layer needs to have some functionalities to do on sending a message. So he already received the message from the top layer, and now he's going to do something on the message and hand it to the next layer. So that's the idea. Each layer receives a message from previous layer, does something on that. It has some responsibilities, and after that sends the message to the next layer. So that's the idea. So it goes from the top, very top, goes to the bottom. Each of them does something on that. Physical layer sends it over the real network, which is the real network here is message is a cable. So very simple case, just assume these two computers are connected through a LAN cable. So it's very simple case. So and the other side receives a message. Again, each layer knows what type of information he's looking for, just receives those type of information, makes sure the message is the correct message, and just pass it to the upper layer. So finally, let's say the messaging application on the other side gonna receive it. So already we discussed about the application layer. So the application layer actually receives the message and creates a message and sends it to transport layer. So now transport layer. So there are some responsibilities for transport layer. Let me go to this slide so we can just talk about this. So transport layer does basically three basic things. First is data integrity. So means let's say I'm going to send a not just message. Let's say the application I have, it is a large file. So I want to make sure this file just sends as a whole file. I mean, so I just send this file to this transport service, and transport service just sends it to different messages, because you cannot send the whole file in the one big message. So that's the transport layer does. So transport layer just make sure, okay, the whole file gonna be sent. Let's say the file is the image, so I'm going to send a message over the image over the message to my friend. So I just send this message to the transport layer. Transport layer makes sure this image in general, in whole message gonna be sent over the network. Or timing. So I want to make sure my message goes on time, exact time what I want. I want to put some delay, make sure the maximum delay gonna be, let's say, to send this message gonna be, let's say, 5 seconds. I gonna make sure my message gonna be delivered to my destination in 5 seconds. So these things gonna be handled in transport service layer. Next step is after transport is network layer. Let me just go back to show you okay what's going on because I don't want to lose the track. So now the application layer. So let's say I send a message. By message here is an image file. I send it to transport layer. Now transport layer makes sure, okay, for example, for now we don't have any timing issues, but add some information to that message to that image and say this is the network layer. So let's see what's the network layer. Network layer. Because I don't want to lose the track, I'm gonna go back to the. Again, this slide. As I said, you can just there are a few examples of what are the services transport service provides. You can just go to the detail here. So now in the network layer we have two. Okay, so let's say we receive the image, and we are going to send it through the network. So basically, and based on the specifications transport layer mentioned, for example, the timing. So let's say my message, as I said, transport layer told me, okay, so I don't have any timing issues for this message. So you can just either use TCP or UDP to send a message in the network layer. So TCP basically means when it provides more functionalities compared to UDP, and make sure your message gonna be received at the receiver. So let's say transport layer told me I want to make sure this message is gonna be received in completely received. I mean, so it's a text message or an image. So I'm gonna use TCP because TCP we're gonna go through this TCP more detail later on. But for now, just assume TCP provides this service as I said, reliable transport. Makes sure the whole image gonna be delivered to the receiver. But UDP on the other side does not guarantee that okay the message is going to be delivered. So as I said, these two network layer protocols, they have different functionalities, they work differently, and they promise different deliverables. So that's the idea. So network layer, decide depending on what you have in transport layer, what you decide about your message, you're going to use either TCP or UDP to send your message. So after you decide this TCP, UDP, let's say I'm going to go for TCP. So TCP going to add some specific fields to your message now because you are using TCP. As I said, for example, he is going to make sure you are using a reliable transport. So for having reliability, as Dr. Lang mentioned, you're going to have some sequence numbers. You're going to have some fields later on. You're going to for details. There are some bits said on the message. So we're going to add few information to the original message we received from transport layer. We're going to add few more information to that. This information going to help us, help the whole network to deliver my message reliably. That's the idea. That's why we need this TCP, because this TCP adds more information to the original message, which is, let's say in this example, an image I received, adds more information to make sure through this network, let's say through the internet, my image gonna be transferred reliably. So that's the idea of TCP. So UDP is the same. So that's the idea of network layer. So next step after this network layer, after adds this information, hands the data now to the. Let me go back to this slide to show you exactly what's going on. We don't lose the track. So now, as I said, image went to transport, added some information, went to the network. For now, let's say we assume we are using the TCP. So TCP now sends a message to the link network. Link network. And also, sorry, in the network, I forgot to say. Also, as you said, Dr. Lang mentioned about IP addressing and everything. All of them can be handled here. Now, link network, let's go back to the link network. See what's going on with the link, if he has a slide. Otherwise, I just go by myself. As I said, this TCP, you're going to receive it. So I believe for link and physical layers, he's going to explain it in the future slides. So for now, I'm just going to give you very short brief about what's going on also in the link layer. So link layer means, let's say you are in the LAN network. So you are going to send a message over your LAN, not to go to the whole internet. So the link layer handles that. So also this link layer adds few more information to the packet, and sends it to the physical layer. Now the physical layer is the layer actually responsible for physically sending the data. So I mean converting the data to the physical waves. Let's say you are using wireless. So you have a wireless card on your system, yes. So that wireless card means the physical layer. That's gonna receive a message. The packet now after this link layer, the packet, because we have the packet, all the informations are in the packet, and we're gonna receive this packet and convert it to the, let's say, wireless signal, send it through the wireless signal to the air. The other side, the physical layer, which is in this case, let's say for example, wireless card, gonna receive the message and again hand it to the link layer. Link layer already knows what type of information he is looking for, looks for those information, extracts those information, and hands the rest of the packet to the network layer. Network layer extracts its own information, which this side the network layer already added. This side, receiver side, gonna extract those information and make sure, let's say, for example, it's a TCP service. As I said, TCP now wants to make sure he already received the whole message. I mean, as I said, the whole image he already received. So if, based on the information the sender already put in the network side. So if he realizes that, okay, I received the whole image, the messages, the integration of the message is okay, he just hands this message to the transport layer. And transport layer sends it to the application layer, which is right now, the messaging app running on my friend's computer. So that's the whole idea. I know it's because it's very, I'm pretty sure Dr. Lang gonna go to each layer very much more detail, because each layer actually has some tasks, some fields, but overall that's the idea. Because we're gonna make sure our message gonna be received in the receiver side, we're gonna add some information through these layers. Each layer has its own information, and the other side gonna, based on the information the sender already added to the packet, the receiver gonna use those information to retrieve the message and make sure, let's say, the message is sent on time, or the whole message already received, I do not miss anything. So that's the idea of these 5 layers. But don't worry, for now you're gonna go through each layer in much more detail later on through the slides.